All right, now let's work on the notes for Unit 7.1, which is all about balancing these chemical equations. Remember how I said with the Legos that the law of conservation of mass is very important. In fact, I would even jot that down somewhere. Law of conservation of mass. It means matter is neither created nor destroyed in a chemical reaction. I'm just going to call it matter. Matter, mass, same thing. But matter is not created or destroyed during the process of a chemical reaction. It just changes form. Super important. Okay? Because of that, when we write these chemical reactions to show a chemical equation, they have to be balanced. They have to be written in such a way that I have the same number of Lego pieces in the reactants or the ingredient side as I do in the product side. Okay, so it's the same number of pieces, the same number of atoms, just arranged in a different way. Right? So that's what it says here in our introduction. It is important to balance chemical equations properly because balanced equations are useful for calculating amounts of each compound or element, blah, 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 that are needed. This is the important part, that are needed or should be produced during a reaction. Okay? When you are working on a recipe, let's say you're baking a cake, right? It is important to know the ingredients that are needed. It is important to know the amount you are going to have at the end, right? You can't just random throw stuff together and assume it's going to be a cake. Baking especially has to be very exact. The chemical reaction that happens in baking is very important that you measure out exactly the right amounts. Okay? If you're needing to feed 20 people and you bake a cake that's only going to feed 5 because you didn't figure out how much is going to be produced, how big your cake is going to be, you're going to have some hungry, angry people because there's not enough cake. Right? So with these chemical equations, same thing. It is very important that we know how much stuff is needed, how much ingredients we need to start with, and how much is going to be produced, what our end product is going to be, and how much. Right? So these balanced equations are incredibly important. Here is how we do that, and then you guys are going to do a bunch of examples. Okay? So first, just sort of get an idea of what reaction is going on, right? What are the ingredients? What are the products? Are they gas, liquid, water, solid? So just get an overview of the equation or the reaction that is happening. Excuse me. So here's our example. We have it's photosynthesis. You all know about that from biology. So we have solid glucose, which is C6H12O6, that's the chemical formula for glucose, is burned in the presence of oxygen. So the plants take in oxygen, and that produces, I guess this is the opposite of photosynthesis, huh? This is respiration. Sorry. I thought we were making glucose, but we're using it as one of our reactants. That's what I get for not reading the reaction. That's why we do step 1, so we determine what's going on. So this is cellular respiration. We got glucose and oxygen, right? We take in food, we breathe. That produces carbon dioxide, we breathe out, and water vapor, which also gets breathed out. And just for informational, for every mole of glucose burned, 2,800 kilojoules of heat energy is produced. What do we use that energy for? A, it keeps our body temperature up, right? B, our muscles use it, convert it, so we can move and think and do all the other things we need to do during the day. So cellular respiration is what's going on here. Let's detail that out a little more. So we have 2 reactants. We have glucose. We'll just write the chemical formula, C6H12O6. and oxygen. So, and O2, that's oxygen. Right? Those go through a chemical process, and what we end up with produces carbon dioxide, CO2, and water, H2O. So now we've figured out what's happening. Step number 2 is we write out the unbalanced equation. So we don't worry about anything like how much glucose, how much water. We don't worry about that just yet. We're just getting the ingredients and the products written down, right? Like if we were talking about baking a cake, it'd be like a flour, sugar, egg, milk makes cake, right? We're not going to worry too much. How many eggs? How much flour? Not right yet. Let's just write down the general equation. So reactants always go on the left. So we have carbon or glucose, C6H12O6, plus oxygen, right? Then the arrow means chemical reaction took place, right? And over here we have carbon dioxide plus water. Okay, so there's our general equation. Now we need to balance it. Because of that law of conservation of matter, we know with this equation it's got to be balanced. I have to have the same amount of carbons on the reactant side that I do on the product side. I have to have the same amount of hydrogens on the left that I do on the right. Same amount of oxygens, but it's all got to match up. And like anything else, there are hundreds of different ways to do this. I'm going to show you my way. I usually don't like to use a piece of paper. I usually like to use a whiteboard, a little whiteboard or something, because it's easier to erase. But that's okay. We'll do it here in our notes so you have it written down. So the first thing I do is where there is an arrow, I make a line. Boom. Reactants, products. I have them on either side. Okay. Then I make a list. What are all my elements that I have over here? I have carbon, I have hydrogen, I have oxygen. And then I look on this side. I have carbon, I have hydrogen, I have oxygen. Carbon, hydrogen, oxygen. Okay? Then, how many? How many carbons do I have on this side? 6. How many hydrogens do I have on this side? 12. How many oxygens do I have on this side? I have 6 here. I have 2 here. That makes 8. Boom. Over here, I have 1 carbon. I have 2 hydrogens. I have 3 oxygens. 2 over here, 1 over here. Makes 3. 1, 2, 3. So this is how many I have. Remember, by the end of the process, these numbers have to equal. Okay? So they've got to equal each other. Really, this is just like a puzzle, y'all. You know, sometimes you do those puzzles and you try something and it doesn't work, and then you erase and you try something different. It is just like that. Even I have to try different things. Sometimes I get them quicker than others. There are some things that I know through practice, but it really is just like a puzzle. So just because it's on top, I'm going to start with the carbons. Okay, there are 6 of them over here. There's 1 over here. Okay. So to make that balance, I need to make sure that there are 6 carbons on my product side. The only way, let me repeat that, the only way, let me say it one more time. The only way that you can change a reaction is by putting a number out in front. I can say how many carbon dioxide molecules I have. I cannot put a subscript 6 right here, because then this is no longer carbon dioxide. It has to remain carbon dioxide. But I can say, well, how many carbon dioxide molecules do I have? Let's go back to my Legos. like with the Legos, we can see 1, 2, 3. There are 3 red Legos, right? I can't change the color of the Lego. It's red. It is what it is. These are yellow. These are blue. This one's orange. This one's green. It is what it is, white. I can't change the color of the Lego. I can change how many, right? Now I've taken off 2 blue Legos, so there are fewer blue ones in my thing. I can add, but I cannot change the color of the Lego. I cannot change the carbon dioxide molecule. It is what it is. I can change how many of them I have. So, in order to balance my carbons, I need to say, well, on this side of the equation, instead of just 1 carbon dioxide molecule, there are 6 of them. So I can change the amount to 6. Now, so you're going to see in a minute why I like doing this on the whiteboard. Now I have 6 carbons over here. But by changing the amount, I also changed my number of oxygens. So now over here, instead of 3 oxygens, I have, 6 times 2 is 12, right? And 1 more is 13. I don't even need to erase. Now I have 13. Fine. We'll get to that. Don't worry about it. It's a process. Next, hydrogens. 12 over here, 2 over here. Okay? Well, I need to do something over here to make there to be 12 hydrogens. Again, this is water. I can't change it. It's got to stay this. But I can say how many waters I have. So if I put a 6 right here, 6 times 2 is 12. So with 6 water molecules, I have 12 hydrogen atoms. So I've changed the amount to match it up. Again, that changes my number of oxygens, but you'll see in this example that that's actually a good thing at this point. Now, my number of oxygen atoms, I have 12 here and 6 here. What is 12 plus 6? 18, right? So now instead of 13, I have 18. Okay? I'm getting there. My carbons are balanced. My hydrogens are balanced. My oxygens are not balanced. Okay? So, oxygen is either here and here. Right? If I change the number of glucose molecules, like if I put a 2 right here to make there be 12 oxygens, or a 3 to make, it messes with my carbons, it messes with my hydrogens, right? So let's just leave this a 1. Because I have oxygen over here all by itself, I can change this number, right? So that I have 18 oxygens over here. So you might think first off, oh, there's 2 oxygens here. So to make 18, we need 9. Okay? Yeah, that's a good thought. Ooh, but don't forget these 6 over here. So if I make 18 here, I have to add this 6 to it. Right? So really what I need here is 12. Because 18 minus these 6, I need 12 more. Does that make sense? If it doesn't, rewind and listen again. So in order to make 12 oxygens here, I want to put a 6 right there. Remember, I can't change this. Can't change the molecule. I can just change how many of them I have. Now, my oxygens, I have 6 here, plus 12. 6 plus 12 is 18. So I have 6 carbons, 12 hydrogens, and 18 oxygens on the left. 6 carbons, 12 hydrogens, 18 oxygens on the right. My equation is balanced. Okay. Again, there are hundreds of different ways to do this. If you want to draw pictures, if you want to, how it makes sense to you. Like I know some people like to draw it out. There are 6 carbons. There are 12 hydrogens. And so they work through it that way. If you want to take Legos, make the red one's carbon and the blue one's hydrogen and the green one's oxygen and set them out and then figure out how many you need, go for it. That is definitely another way to do that. But again, it's just a puzzle, and you have to work through it and do the best you can back and forth. Your homework for this lesson is to practice doing a lot of these, so you'll get the hang of it.